Welcome to another stream. Today, two things. First of all, I'm not prepping for interviews, I'm just learning stuff. So, and relearning stuff. So, I can remove this. What I'm gonna do now is try to implement a linked list on my own. Of course, I'm gonna try also to explain my thought process through all of this. So, nice. Nice, nice, nice. I'm just gonna continue here. First thing, let's start with some theory. I'm just gonna increase this, create a mind map. Yeah, mind map works the best for me when it comes to remembering stuff. So this will be where is the center? It's here somewhere. This will be a linked list topic. I'm just gonna create a bubble. And let's set. So, what's a linked list? It's a data structure that represents a sequence of nodes. So, it's a data structure that represents a sequence of nodes. Now, in a singly linked list, each node points to the next node in the linked list. And we have also another type of a linked list. So we can have a singly linked list or a doubly linked list, and the difference between them is the way they behave. Basically, in a singly linked list, each node points to the next node in the linked list, and that doubly linked list gives each node pointers back to the next node and the previous node. So basically, if this is a node. Wait, let me draw this better. So what's this? A linked list, a node. It points to the next element. This guy points to the element after this. And this would be a singly linked list. But if I wanted to create a doubly linked list, I would just create a pointer to the previous element. But I'm just gonna leave it as it is. And maybe just right here, so I know that this is a singly linked list. Okay. So what is a linked list, and what's the difference between a linked list and let's say an array? So we don't have direct access or constant time access to any particular individual node within the list, or index, as we would say in an array. So what happens is that if we want to find, like in this scenario, if you want to find any element, for example, the last element in the linked list, we can just say linked list 0, 1, 2, because this won't work. We will need to iterate through all the elements in order to find this element. All right, let's implement this. Let me just move this out of the way. The title will be linked list. Let me insert the code. And let's start. So again, a linked list is a data structure where each element, and the element is called a node, is connected to the next one using a reference or a link. And unlike arrays, the elements are not stored in contiguous memory locations, as we just mentioned that. And basically the structure of it, let me just write this again, maybe it will. How it works is that we have data, which is in this case 1, and we also have the pointer to the next one, which is in this case 2, and then we have again data, which is 2, and next, and data, which is 3, and next here. All right. So let's implement this guy in Python. Let's start by creating class node. Node is the individual element, so we definitely need it. So node. Let's create the initializer. The initializer is gonna have self, it's gonna have data. So data will be the data that we provide. Next is none for now, because we don't know the next element in the linked list. What else? I think that's it. The next thing is what have I done here? I made a mistake. I made a poopy. Can I remove this? Yes, I can. So linked list. Again, we are initializing it. So we need a head. Initially, the head will be. We won't have a head. We won't have a first element because we need to initialize it later on. And then we just need to create append self. Can I zoom this in a bit more? This too much. Self. We have data. So what happens here is that we create a new node out of the data that we provide. All right, this is easy. So if we don't have head, I'm setting the head to be the new node. I'm setting the head to be the new node. Otherwise, I'm setting the head to be the current node through which we are gonna iterate to find the last point where we don't have the next pointer, and there we will insert the new element. So while we have the next element, I'm just doing this. And I'm setting it here. Seems relatively simple. Okay, what other methods do we need here? What other elements do we need here? Maybe we could also create a function to display nodes. So we have current is gonna be head, while there is a current, while we have elements in the linked list, plus print data, this. Why do I have an error here? Because I need to set this to be equal to. So basically, end is just the content that we append after we print out our data. So current is equal to current next. Then I just print end, and that's it. And now if I why I'm creating these extra contents, even though I don't need them. So yes, easy. What else would I need here? So maybe we could try to implement a deletion process, deleting a node from a linked list. So we need to find the previous node and set the previous nodes next to be equal to the pointer after the previous node. Basically, what we need to do, if you take a look here, let's say we are removing the 2 and we come across 2, so we find the previous node, which is this one, and we set the pointer of next to point here at the 3. So this 2 is no longer in the linked list at all. Of course, if we have a double linked list, we need to update both the previous pointer as well. Okay. So let's also implement this as well. All right, let's do this. All right, so what should we do here? We need to find a loop to find the node whose next node contains the value to be deleted. And then if we found the value, we are going to update the next pointer of this node. So yeah, it sounds a bit complex, but it shouldn't be. Let's do this. Self value. So what should we handle first? An empty, not self head. If there's not a head, print list is empty. All right, and return. What else do we have here? So if we have only one element, and this one element self head data is equal to the value we are searching, what happens here? So in this scenario, we have the following thing happening. If we want to delete the head, the first guy, we are setting the head because this is not only an element in the linked list, it's the first element, it's the head element. So we need to set the head to be the next element because we are deleting the first one. So head self head next we print deleted node with value return. Okay, now we have the general case. So in the general case, we need to traverse the list in order to find the node. So parent is equal self head. Now, while there's a next and current next data is not equal to value that we are searching for, okay. And then we just do current next is equal to current next. I'm just gonna copy this here. So what other case we have? If the node is not found, if there is no current.next, print no node with value found. So let's delete a couple of elements. Oops. If I run this now, no node with value 40. Oh, we have an error. I have an error here. Nice. So where? I try to delete this element, which is not found anywhere. I forgot to return. Basically, I tried. I was checking properly whether we don't have the next element, but I forgot to return the execution. So what happened is that we came to the next line and we tried to access the next element which isn't there, and that's why we got an error. Yeah, no node with value 40 found. All right. So let's write. Let's solve a couple of examples here. The first one is saying the following. It says here, let me just write this, markdown. Write code to remove duplicates from an unsorted linked list. And how can we do this? Dumb. So it's gonna be a new method. Do I need to put it here directly? Should it be under the linked list? Yeah. Let's put it here. Hey Aaron, what's up? How can we do this? Again, let me just copy this. If we don't have a head, the list is empty. Otherwise. How can we need to keep, okay, let me just write this. Maybe it's gonna be. So how to remove duplicates. How to remove duplicates from a linked list. So we need to keep, we need to have a data structure. Need a data structure that is keeping track of the elements we have already seen while traversing the list, because we want to keep this running at OM time. So we need something. We need to basically make only one iteration through the linked list. Okay, how can we implement it in Python? Let's start. We start scene elements. Let's create the current element. Let's add current the current node's value to the list of scene elements. So while we have a next one, if while we have the next one, let me just draw again. Maybe it's going to be easier both for me to understand it better. So let's say we have a 3 and a 2 here. So if we came across this node, and next we check for the next element in it and the data of it, which is 3, and if we have this in our scene object, which is consisting of currently, let's say, 1, 2, and 3, and if we have it here, we can just skip it by moving the pointer of this 2 to this 2. Again, this 2 is also a duplicate, but I just wanted to show you an example directly on one of the elements. Let me remove this and this and this. Hey, what's up? If I have data, so if this is in scene, I'm just moving my pointer to the next element. Otherwise, I'm adding the data in our scene data structure. And I'm doing this. I think this should be okay. Let me do this as well. Let me do this again. I'm gonna comment out these lines. I don't need them right now. And then I'm gonna remove duplicates, save, run. So we have 10, 20, 30, 30, 20, 40, 10, 20, 40. And in the end, we only have 10, 20, 30, 40. Yeah. Yeah. Okay, let's do another example, another problem of it. Okay, so let's do another example. He says partition a linked list around a node, around a value x, such as all nodes that contain a value that's less than x come before all nodes that are greater than or equal to x. If x is contained within the list, the values of x only need to be after the elements. Okay, so this is the problem that we need to solve here. The way to solve these kinds of questions is where we need to partition a linked list is to divide the linked list into multiple linked lists, and we have partitions that are containing all the nodes with values that are less than x, and partitions that are containing all nodes that have values greater than x or equal than x, and then finally we merge them. So how can we do this? Let me write an example here. So what I need to do here, is my tablet on? It is, but for some reason it's oversized. And now it looks good. I didn't have the time to fill in all the boxes, but what we should do here is create two partitions. For example, if we are looking at 6 here, what we need to do is find nodes with values less than x, which will go into left partition, and greater than x, which will go into the right partition. And then we need to traverse the list. And for each node, we need to append it to either one of the partitions. All right, and then we merge these two partitions, and I think that's it. I don't think there's much thinking there. So what's the complexity of this? So the type complexity is either on, because we visit each node only once. What do we have for space complexity? We don't create any specific data structures. We are only manipulating references to nodes. All right, let's create a left head, which is none, right head, which is none as well. We set the current to the self head. All right. And while we have current, I'm looking at the next node. I'm taking the content of the next node. And I need to disconnect the current node. Current none. If the data of the current node is less than x. But wait. Because what happens here is also I need to create two nodes. Like this. I'm not gonna even create. Let's do this. And this is the second one. I need to connect them. So I need a pointer as well. It's gonna keep track of the last node in the first partition. All right. I need that as well. So let me revisit this. So I have left head is gonna be equal to left tail, because the left tail will be grafted on the right head. Do I need the right tail? Let's add it. So if the current data is less than x, so if we have chosen 6, what happens? If we have chosen 6, the tail will hold the current, will point to the current element, right? Because what happens here is the following. We have a linked list, and we check if the current data is less than X. So, okay, we break the chain. We break the pointer chain. And we have the left partition, and we set the next element to be equal to the current. And then I set the current to be equal to the left tail. Okay, so, oh, but I also need to, if we don't have the head, so if we don't have the head, I'm setting the left head and the left tail to be equal to current. So this is only the first time. But otherwise, I'm doing this. So basically what happens here, maybe I can visually explain it better. Let's say we have 5. And because we don't have the left partition, both the head and the tail are at 5. But then we come to 2. So what we do here is that we set, because the tail is at 5, we set the next to be 2. So we set a pointer, and then we remove the tail and we put it at 2. All right. And you're gonna go, we are gonna do the same thing in reverse as well. All right. Otherwise, wait, where is this else going? Yeah, it's going here, I think. It's okay. Otherwise, if you don't have the right head, so what should we do? Same thing, right head, right tail, current. Otherwise, if we have it, right tail, next is current, right tail, current, and then we are setting our current to be the next node. And that's it. The only thing we need to do is to merge it. If we have the left tail next is equal to the right head, and the self head is left tail value, no, only left tail. Otherwise, I'm just setting the head to be the right head in case we only have elements that are bigger than what we have. So I'm gonna comment this out, and I'm gonna put here 5, 7, 2, 6, 1, 9, 10, and 8. Let me just remove this. All right, and now if I do the following thing, if I do partition. And if I do play again, what's happening? We should have the following thing. Before I even show the code, we should have the following thing. We should have 5, it will point to 2, it will point to 1, it will point to 6, which will point to 7, 9, 10, 5. No. Oh, we have an error here. We have an error here. Amazing. Ah, we need a value. Okay. 6. Ah. 1, 7. Where is the 2? Where is the 2? Where is the 2 here, my friend? Mi compadre. Where is the 2? What have I not done properly? This is okay. This is okay as well. I think this should be right. So this is an else to this if we don't have the right head. I think this should solve it. Yeah, we have the 2 again. So what was happening here was that we had already the 2, I think, and the 2. Let me just run this again, see what's happening. Ah, no. Left head. So if I run it again, 5, 2, 1. Yeah, this is the correct behavior now. Let's save this. So should I do another example? Let me just open my other project. This is the one. So now let's do something else. Let's talk about some deep learning concepts. This is my first introduction to it. I worked a bit with some, let's say, deep learning algorithms like neural networks and paradigms like neural network in university, but a long time has passed since then. So I'm rusty. I'm really rusty. And where did I stop? I think I stopped with functions with multiple inputs. Yeah. So I'm just gonna do a quick review of everything. I can turn this down. Why? Where's the content? Wait. We are having slight technical difficulties for some reason. I don't see my tablet. No. And now, okay, we have it. Ladies and gentlemen, we got him. Where did I stop here? Yeah, I stopped at functions with multiple inputs. So the last couple of, not episodes, but more tries in which I try to understand this, I think I got the gist of it, in which we have a function that calls another function, and we have these all different inputs that are entering here. They are being manipulated, they are being converted, they are entering the other one, doing the same thing here, doing the same thing here, and also there's the rate of change in which our input values are changing. But now we have functions with multiple inputs. So we have multiple inputs, and we have a simple scenario here in which I have the inputs x and y, and the function is occurring in 2 steps. So we are starting with the math here. If the inputs are x and y, we can think of the functions that's occurring in 2 steps. X and y are fed through a function that adds them together. It's this function right here called alpha. Is this alpha? I think it is. And then we feed the result of this function, which is a, into another function rho, which is whatever function we want. And the input of this is s. And equivalently, we could also write this as here. Oops, I removed it even though I didn't want. Like here. So what we need to do now is okay, I need to code this up now. Where am I? Where's my, yeah, it's here. I can remove this. Okay, so simple enough. Now, let's talk about the derivatives of functions with multiple inputs. So we can also compute, of course, the derivative of the output of a function with multiple inputs with respect to both of its inputs. So conceptually, I can do something like this. Maybe just add on this diagram that we have here. So A is coming back, and we are creating this alpha over x of this function containing x and epsilon, and the same thing here, but the only difference is that we are creating this for rho, y for a. And basically it's the same thing. Now, what we have here is the mathematical representation of having a function consisting of x and epsilon as its argument, which goes first to the row method, and then to the alpha method. And of course we take the parameters x and y. So how is this translated? Can I get a bit more fire on this? Maybe like this. So what do I have here? This is equal to df or dx is rho over u of alpha x and epsilon multiplied by d alpha over dx of x and epsilon. So let's code this out. So let's multiple inputs, derivative, x is an ND array, epsilon is an ND array. We have sigma, which is a function, returning a float value. So how will this work? I need to compute these for both x and epsilon changes. So a is x plus epsilon. And then I have the derivative, which is derivative of this value to a daddy. Oops. So, but why is this like this? So, what I'm trying to understand is why do we have here dA, dx, and dA and that equal to 1? So, I mean, this is a pretty simple function. Just x and y are inputs, and their sum is passed to another function, which is... Wait, this is sigma. This is not rho. Why have I thought for the whole time that this was... It's sigma. Oh god. All right, my bad. So this is sigma. So we pass the sum of x and epsilon inputs into another function, and it's most probably some kind. Hey, the great Indian analyst, what's up? Good. It's still actually running. It's 5:30 where I'm from. So I was thinking to do a stream because I started learning deep learning, and it's really interesting to me, even though I don't understand anything. And it just proves how much stuff I forgot in university. I knew a lot more when it came to math and everything. So yeah, I was thinking to do maybe, I don't know, 1 hour of this, maybe 2, and then I'll probably say bye and go out, enjoy my night. It's still early, even though it's dark. So, what I'm trying to do here, my friends, is to understand why is this derivative equal to 1. So I get this. I get this. I get why we want to compute how sigma of A is changing and x and epsilon is changing. So, and also the chain rule. The chain rule is simple because it's not simple, it's built into math as it is natural to the concept of derivatives. So if we have a function, if I have a function, where are you? You are here. If I have f of g of x, so what will we have here? So, sorry. So if this is the function, the chain rule of this would be df over dg times dg over the derivative of x. So in our case, what we have is this function, a is equal x plus epsilon, which is the inner function. And we have the sigma, which is the outer function. So how is the chain rule working in this scenario? I think I get it. So wait, let me. So this is the formula. This is the formula on how this works. Here we have that a is equal to this, and this is actually our inner function, and our outer function will be f of a, which will be sigma. I don't know how to write sigma. Of a. And then we need to expand this to do a derivative on both, for both x and epsilon. So why is the derivative of a for x 1 and derivative of a for epsilon 1 as well? Okay, so I think I get it. So because this is the function, and when we do the derivative for x and for epsilon, because they are both linear once we derive from them, they're only gonna be 1. And when we compute for x, epsilon is treated as a constant. Okay, I need to refresh my knowledge on derivatives, definitely. All right, so this is basically just math, because Right, so here we actually compute the derivative for the sigma function. I'm computing the derivative for the sigma function. What am I doing next? So it's dA. Oh, it's not. It's d sigma over dA. So that's it. But these two are ones because our input function is x plus epsilon. So I'm just computing the final outputs, which are the derivatives with respect to x and epsilon are these two. All right, so I think I understand the math behind. Basically, let me just write it here. So I'm just gonna write it so I don't forget. So the chain rule. Chain rule computes the rate of change. Change of a composite function f g x. All right. But for functions with multiple variables, we need to account for all the ways the output of the function depends on the input. So that's why we expand the chain rule. V x expand chain rule. So because the sigma of A depends on A, and A depends on two inputs, x and y, we expand the chain rule because sigma of A indirectly depends on both x and epsilon via A. So let me just do this. Let me maybe write in red. Okay, red is too strong. Maybe it is orange. All right. So what do we have here? So we have sigma of A, which the output depends directly on A. And then I have A is equal x plus epsilon, where the variable depends on these two guys, x and epsilon, right? So I want to calculate the derivative of sigma with respect to x and the derivative of sigma with respect to y, because I have two variables. I have x and y. So to compute this, I need to see how. So I need to see how the derivative changes with respect to a, which is our, let's say, our parent method. And then I calculate the derivative for x. And then I do the same thing for here, the only difference being I'm using epsilon instead of x. Let's do an example. So instead, let me just show this. Instead of having a a lot of space here. So instead of this is gonna be an example. So instead of having a in which we add x and epsilon, I'm gonna have a in which I multiply x and epsilon, and I have sigma of a say squared. So we need to compute the derivative of this with both respects to x and epsilon. So the derivative of sigma over the function a will be 2a. But now we also need to compute the derivative of a over epsilon, in which what will have only epsilon, right? No, for epsilon we will only have x, and for x will only have epsilon. Because we are treating x and epsilon as constants with differentiating with respect to x and epsilon. And then we need to combine the results. So the derivative for sigma over x is 2a times epsilon. And then we are substituting, instead of a, we are using 2x epsilon times epsilon. It's going to be 2x epsilon squared. And the same thing is going to be here for epsilon. It's going to be 2a times x, right? 2x epsilon times x is going to be 2x squared epsilon. All right, let's talk about something else here. So let's talk about functions with multiple vector inputs. I'm just gonna, oops, clear this so it doesn't bother us. So it's functions with multiple vector inputs. Okay. So what do we have here? So in deep learning, functions functions that are used are mostly functions whose inputs are vectors or matrices. All right. So in deep learning, inputs are vectors or matrices. So we also need to understand the logic of the chain rule and computing the derivatives using these inputs. So in deep learning, our goal is to fit a model to some data. The goal is to fit a model to some data. So we need to find a mathematical function that maps observations from data, which will be inputs to the functions, to some desired predictions from the data, which will be the outputs of the function in an optimal way as possible. All right. What does this mean? So it turns out these observations will be encoded in matrices, and typically we throw as an observation in each column as a numeric feature for that observation. We'll cover this in more detail. Okay, not now. So in deep learning, we are trying to build a mathematical function that takes input data and makes predictions. For example, have a picture of an animal, no, of an apple. And this is the input. And the output is the model, which will predict whether the picture is, I don't know, an orange or an apple or something else. So the goal is to make these predictions as accurate as possible by training the model on the data. And for this, we use derivatives. And why do we use derivatives? why do we use derivatives? In order to improve the accuracy of predictions, the model needs to adjust itself over time. And the adjustment is done using derivatives because derivatives tell us how much the output changes when we change the model's parameters, like weight or biases or something, and which direction to move the parameters to make the predictions better, so to minimize errors. And so, all right, functions have multiple vector inputs. So in DL, inputs are vectors or matrices, and the goal is to fit a model to some data. So basically, we need to use derivatives. We need to, in deep learning, we are building a mathematical function that takes input data and makes predictions. For example, we have a picture of an animal, and the output is some model that's predicting whether the animal is a cat, dog, or something else. Prediction. And the goal is to make these predictions as accurate as possible by training the model on data. And we use derivatives for this because we want to improve the accuracy of predictions and because the model will adjust itself over time. And the adjustment is done using derivatives because the derivatives tells us how much the output changes when we change the model parameters and which direction to move the parameters to make the predictions, better to minimize the error.